So almost exactly a year ago, I embarked on a journey to take my desktop, my laptop, and my phone off of the IPv4 internet. I went IPv6 only for 1 week. Video up here where I did that. But after that week was over, I went back to my normal network, my normal LAN, that was still there and still running everything as it had been. And that's how it's been for the past year. Over that time, I spent a lot of work in hopefully dual stacking all of my hosts, looking at all of my virtual machines, containers, making sure they're all dual stack capable to run IPv6. And now I think I'm ready to take the next major step in converting my regular home network into an IPv6 only or mostly network. So there's something like 60 or 70 devices on my network, and I'm going to go through them system by system and systematically move them over from legacy addresses to modern addresses. That's not going to all be in this video, but I'm hoping by the end of the video I can have at least 10 devices that are IPv6 only on my home network. Everything is still working, and then in future videos I can migrate more and more devices, I don't know, maybe 5 or 10 at a time, get rid of their legacy addresses, move them v6 only. So if you're interested in IPv6 and OPNsense and macOS, come along on this adventure. So IPv6 deployment is really the tale of two internets. We have the IPv4 internet and the IPv6 internet. Even back in the 1990s, engineers realized that the addressing methods of IPv4 could not scale into the future. When the web era emerged, we needed a better solution, and that solution was IPv6. Nevertheless, for about 20 years after that, we continued deploying things as IPv4 primary. The expectation was that everything on the internet would be accessible over IPv4, and a lot of it would also be accessible over IPv6, but if you only had an IPv4, that was still okay. Now, one of the challenges is that IPv6 and IPv4 are not intercompatible. We can't directly translate between them. So for clients to be able to access IPv4 resources, the clients need IPv4 addressing, and for clients to get IPv6, they also need IPv6 addressing. So early on in the v6 transition, the early adopters started using tunneling technologies. Their service providers didn't carry v6, so they would tunnel their v6 traffic over to some relay, using a protocol like 6RD, ISATAP, or Teredo tunnels. Now these early adopters were able to get v6 connectivity to the modern world, but they pay the early adopter tax, latency. You see, every time we go through an extra step in the process, an extra route or an extra tunnel, we're breaking the direct end-to-end path, and we're introducing latency. So in IPv4 we have network address translation, which forces all of our traffic to go through a NAT gateway and adds a bit of latency. But in something like ISATAP or 6RD, our packets are going way the hell out of the way to a gateway, and then they can go back to the v6 internet. So it's introducing quite a bit of latency. So then as v6 started catching on for real, we started seeing actual real deployment in the real world, we started going to dual stack. So now we're providing a full v4 service to all clients, and a full v6 service to all clients. This means our clients can access the whole internet, v4 and v6, using native v4 connectivity and native v6 connectivity. In most of the world, this is what your internet service provider will give you today. But now this brings some other challenges. Now, operationally, we have to support both v4 and v6 everywhere. All of our subnets have to have v4 and v6 addressing, so we need a v4 addressing and subnetting plan and a v6 addressing and subnetting plan. We need to configure our routers for v4 and v6. All of our routing protocols need to deal with v4 and v6. It's a lot more operational complexity to deal with both. And also, we're starting to get to a point where even this is not longer sustainable in the v4 world. With modern internet service providers very much out of addresses, they're being pushed into carrier-grade NAT more and more. And so this is adding some additional latency in the v4 path that the v6 path doesn't have. It also severely complicates the deployment of v4 on new ISP networks. Now, a lot of legacy ISPs have enough v4 space to work with for now because they got in the game early. And a lot of cloud providers like Amazon have been spending the last decade buying up v4 addresses, so they're okay for now too. But that doesn't mean every ISP has enough v4 to go around or even has enough v4 to deploy their CG-NAT gateways. So that brings us beyond the mid-stage of v6 deployment. So depending on where you are in the world, v6 traffic might be as high as 70% in your country. Worldwide average is probably closer to 40%, but it depends on what company does the measuring. So how do we move beyond the full dual stack to a more v6 world. So back in the early days of v6, we used to tunnel v4, and that wasn't the best for v6 traffic, but it meant we didn't have to deploy 2 stacks. So now we can do the opposite. We can deploy only v6 and tunnel our v4. By bringing IPv4 as a service on top of v6, that gets rid of all of the former IPv4 complexity we had in our network, kicks it all out, and now just leaves us to a translation gateway somewhere on the network. So this is the path that a lot of mobile ISPs have already been doing for the last couple of years. Many of them are deploying v6 only across their network, and they're relying on the phones to do v4 to v6 translation, so the network can provide the opposite, v6 to v4 translation. On a bit of a more technical level, what's actually happening is an IPv4 address is 32 bits long. So with a single 64-bit v6 subnet, we could fit 4 billion copies of the entire IPv4 internet address space just into our v6 subnet. So we're going to do just that. We're going to encode the v4 address as a longer v6 address, transfer it over our network, and our network's going to recognize that specific subnet needs to get translated back to v4 on the way out. That translation is called the NAT64 gateway. It's part of our customer edge router, in my case the only router OPNsense. So then what about client side? Well, there's 2 ways we can deal with clients. If the clients respect DNS, they don't actually care if they're getting an address over v4 or v6, only that the address they get works. So for major websites like GitHub that don't support IPv6 yet, we can take their IPv4 address, encode it as an IPv6 address, and return that over DNS. So our clients will resolve the DNS name as a v6 address, connect to the v4 gateway, get sent out to the world through NAT, and they'll never even know that the original service was actually v4. Now for some services that actually do direct IP communication, this won't work. So for that step, we need the clients to contribute as well. So the clients could either be manually verified to be entirely v6 supported. So Apple enforces this on their App Store. If we're doing things like IoT devices, home automation, we can do a pretty good job of mandating that our devices support v6, checking that the minimal amount of protocols we're doing support v6, getting on with our life. So client devices, though, are already doing 4 to 6 translation for mobile devices and mobile networks, so we can make use of that at home as well. So the first step in getting this all up and running is to get that NAT64 piece working. And for OPNsense, we're going to use a tool called Tayga to do that. So let's get that set up. So before I jump right into Tayga, let me explain the 4 open source options we have to do server-side NAT64. Option 1, we have Joule. Joule is developed by NICMX. This is the Mexican local internet registry. I believe it's intended to be used by Mexican service providers for their CGNAT and 464X CLAT deployments. Joule is an out-of-tree Linux kernel module distributed as a DKMS package, so it gets dynamically compiled on your system. It very faithfully implements all of the RFCs required to do stateful NAT64. So you have a pool of IPv4 addresses where your customers are egressing from. You have a prefix, the NAT64 prefix. It does all of that address and port translation along the way. You can segregate customers into different outbound port groups. You can do static inbound routes. So it's kind of like port forwarding from an IPv4 address and port to an IPv6 address and port. You can do pretty much everything in that case. A big downside is that because it hooks into NetFilter sort of indirectly as a kernel module, it pulls packets out early in the process and dumps them late in the process. So they skip the Linux firewall. Now if you're a service provider, you're probably dealing with firewalling in a different way anyway, either with a different box or with black hole routing or something like that. And you're not going to rely on a stateful packet firewall in Linux. But if you're a home user, that's probably a pretty big deal. There are ways around this. If you want to use OpenWRT, Joule is a great choice. You can isolate in a network namespace to deal with the pre-routing, post-routing problem. But since I'm using OPNsense, which is based on BSD and not Linux, this is not an option for me. Next up, if you're a big fan of FreeBSD, they have NAT64 built in, so does OpenBSD. But that doesn't mean we can use it in OPNsense either. It's complicated. So fundamentally, OPNsense is a series of scripts that configure the BSD packet filter, PF. But PF is not the only firewall in FreeBSD. There's another one. It's called IPFW. And the feature set between PF and IPFW is not the same. So IPFW has stateful NAT64 and one-to-one NAT64, NAT46 CLAT functionality all built into the kernel, but it's part of IPFW, not PF. So maybe one day OPNsense could be integrated to configure IPFW for NAT functionality. Currently it's using PF for NAT functionality, and that's why this is not directly supported in OPNsense. So that leaves us with our next two options, Tundra and Tayga. Both of these run in user space instead of kernel space, and they rely on the TUN adapter. So the TUN adapter is essentially used for user space VPN solutions. So OpenVPN relies on this, WireGuard Go, WireGuard on macOS, things like that. We'll use the TUN adapter to create a network interface that's backed by some user space daemon. So in the case of Tundra, we create one-to-one mappings between a v4 address and a v6 address statically and use those. So to deploy this for NAT64, we would first have the Linux do NAT66. So Linux would take our v6 packets, it would do address and port translation to get us down to a single v6 address with a bunch of ports. So it's doing normal masquerade in v6. Then it would feed that v6 packet to the Tundra TUN adapter. Tundra translates to v4, sends it back out. So that is how you would implement Tundra. You can also use Tundra to do CLAT functionality, NAT4.6, it works the same way. Now Tundra is also not currently available on OPNsense, which is a bit unfortunate because I think it's better than Tayga. So that leaves us with Tayga. So like Tundra, Tayga operates in user space using the TUN adapter, except it has a dynamic mapping system. So instead of having a one-to-one relationship between a v6 address and a v4 address, it has a pooled relationship. So in the end, we're still dealing with one-to-one mappings. Every v6 packet and address has a corresponding v4 address. We're not doing port translation and masquerade, we're strictly translating IPs. And this means it's not a complete NAT64 solution because we still need to do that port translation somewhere. But for Tayga, that's done on the v4 side. So in Tayga, we allocate a relatively large pool of v4 addresses. In my case, I've allocated a /20. And every time an unknown v6 address makes a connection to the v4 gateway, it's allocated an address out of this pool, and it will use that v4 address for all of its connections going forward. Then, on the host side, we have it do NAT44, traditional masquerade NAT, for these pooled addresses to go out to the internet. So this is available as a package in OPNsense, but the configuration is not super straightforward, so we're going to want to follow the documentation pretty exactly, and I'm going to go through that now. So I pulled up the OPNsense documentation here on how to install Tayga. We're going to walk through this very exactly. It's important, if you have any issues, come back to this document and take a look at it. There's a lot of steps that need to be followed to make this work. And the first of them is to install the Tayga plugin itself. So this is my test firewall. I'm sure you've seen it in other videos. I'm going to go to System, Firmware, Plugins. So now we need to find Tayga. We're going to add that. While that installs, I'm going to explain a little bit about how the packets are going to flow here. So as I said before, Tayga is in user space and has a TUN adapter. So that means we're going to get a new interface on OPNsense. It's going to have a new set of firewall rules, etc. And under the hood, it's called NAT64. In the UI, it's called Tayga. And this interface is going to have a v4 address and a v6 address. And these are the addresses of Tayga itself. So if Tayga itself has to send, for example, ICMP packets, ICMP too big, ping, time exceeded, those kinds of things, it'll send them from its own addresses. So it needs its own v4 address and its own v6 address. Then on the v6 side, we configure a static route in OPNsense. That'll say all packets from the 96-bit NAT64 prefix get sent to the Tayga TUN adapter to get translated. On the v4 side, we now have an address pool. This address pool is all of the v4 to v6 mapped addresses that are created by Tayga. So we need to create a NAT rule so all of these internal pool addresses get natted when they go out. This is not created automatically. As for selecting your prefix, you have two options here. If you have a static prefix, you can choose to use any 64-bit prefix from your designation. If, for example, you have 2001 DB8 6969/48, you could take the last one of that FFFF, you could take 6464, whatever you want, and use that as your NAT64 prefix. All your functionality will work fine. The other option is to use the well-known prefix, which is 64FF9B:/96. This is specified in the RFCs as being the well-known prefix, and some things may fall back on it if they don't know the prefix or whatever. It also has the advantage of being checksum neutral, so packets that pass through the gateway don't have to get their checksum translated. that is the prefix I'm going to use in this video. I like using the well-known prefix because it makes addresses that are translated very clear. It's easy to remember. Not that you should be remembering addresses, but you can put this prefix in DNS, things like that. The other thing it does, though, is per the RFCs, if you use the 64FF9B well-known prefix, you're not supposed to translate addresses from the RFC 1918 space. So that's 10/8, 172.16, and 192.168. And that could be a problem if you want to use your NAT64 to access your legacy IPv4 devices on your own network. Joule doesn't enforce this limitation. Tayga strictly does enforce this. So now at the install finish, let's come over here to Services, Tayga, and configure it. So Services, Tayga. Here's what we have to configure. I'm going to enable the help here. So first of all, we want to enable Tayga. We probably wouldn't have installed it if we didn't want to enable it. Next up, I'm going to skip down to the v6 prefix and the v4 pool, because once we know these, we can start assigning other addresses within this pool. So as I said earlier, I'm going to use the well-known prefix 64FF9B/96. This does mean that I won't be able to use Tayga to access v4 addresses on my LAN from v6 only clients on my LAN. That will essentially force me to move these clients over to v6 dual stack at least, and I like that, but you might not like that. So for this, 64FF9B/96. Next up we have the v4 pool. So remember in v6, clients will have multiple addresses. They'll probably have at least 2, they might have 3 or 4. And so we need to be aware that this pool needs to be big enough to fit all of the clients that are going to be coming out through our gateway. So on my network, I think I have about 70 or so devices. I'm not sure how many of them are using the NAT64 gateway because I don't have a metric on that. But I wanted to have a pool larger than /24. However many clients you have in your network, you probably want a pool to be at least twice that size, maybe 3 times. So for my case, a /20 is fine. Now I know it seems like we're wasting a ton of v4 space here, but it's transition space, so it's free, right? Yeah, that's right. Okay. I can never remember the funny v4 subnets. Nice in v6, they're always just on a 4-bit boundary. Okay, so 192.168.240. Obviously, you can't have other addresses in this space, but pick something you like. Going back up to the top, we have some addresses we need to configure on our own. So like I said earlier, Tayga needs its own address to respond to ICMP. This is one of them from the pool. So in this case, we'll use 240.1. So this needs to be not in the pool, so we can make it one below the pool. 239.255. So this last one, this is the address that Tayga uses for ICMP responses. This should be an address within your own subnet. If your router has a pool you're using for the routing addresses, you can take it out of that. If you don't, you can pick something within your prefix. We do need to include an IPv6 address here. So Tayga was not a fan of my 6.6.6.6, so I set it to an address in the same prefix I used before with 6464 and 4646 are the 2 addresses. So now at this point, we should be able to route packets to Tayga, but they're not going to go anywhere else. So Tayga is an interface like anything else, so we need to allow packets to go through that interface now. And we're just going to say allow all packets through the Tayga interface and rely on the other interfaces for firewalling. So you can firewall on your WAN side and your LAN side. There's no reason to firewall on this kind of intermediate gateway. So firewall rules, Tayga, add a new rule, pass, v4 or v6, and nothing else. Apply that. So next up, we need to do some NAT config. I know we like to hate NAT. OPNsense isn't going to automatically generate NAT rules for this specific subnet, so we have to do it manually. So first we're going to go here, firewall, settings, normalization. We're going to add a rule, and we're going to choose the Tayga rule. And we will save that. Then we will come to NAT outbound. So if you're already using automatic outbound rules, you have to switch to hybrid so we can manually generate some rules here. And now we have to add a manual rule for the Tayga subnet. Source address should be single host or network, and we type in the network we're using as the Tayga pool. That's going to be a /20. And we leave everything else default and save that. Don't forget to click Apply Changes as well. Every time we edit one of these things, it can get an Apply Changes box. So now at this point, we should be able to access NAT64 from the firewall itself. So let's give that a try. So we're going to try trace route. A lot of places let you type in the dot decimal IPv4 notation on the end of a NAT64 prefix. It's kind of handy if you're typing out v4 translated addresses. So this is what a trace route looks like. The first hop of the path is the v6 address of Tayga, and from there all of our ICMP replies have been translated to v6, so they all have that 64FF9B tag on them. They're actually v4 addresses, so 64.45.60.01. Obviously you have to, in your head, you have to translate from 2-digit hex to dot decimal v4, but probably you don't actually care anyway what the address actually is. It's our path here from where we are here to 9.9.9.9. So now the last step we have, optionally, depending on how you want to configure DNS, it's possible to configure DNS to return this prefix in Quad A records. So if a device requests a Quad A record and there is no Quad A record but there is an A record, it can synthesize the Quad A record with this prefix. And if you do DNS on OPNsense as well, I know some of you like to use Pi-hole or AdGuard Home or something, but if you do it with Unbound, we can do it directly in OPNsense. So you go to Services, Unbound DNS, General, and there's enabled NAT64 support, and we can type our prefix here. So now Unbound will do the synthesis for us. If you're using something like AdGuard Home, which is a really great DNS server, by the way, I'm not sure if they have an option or not. I guess I'll put that up on the screen. Editor's note, they do. It's in their configuration here. So this is the AdGuard Home config. Use DNS64 and DNS64 prefixes. So now we've set up the server side in OPNsense. So if our clients would like to use the NAT64 gateway, they can. Now we need to convince our clients to use the NAT64 gateway. So now for clients. Now we got to get those v4 addresses out of our clients. In my experience, the easiest clients are Linux servers. So you've already seen my video, link up there, whatever, where I show how I do v4 to v6 ingress with HA proxy and TCP mode. So this means that all of my services are coming through. If they come through on v4, they get sent to the right place by their TLS SNI. So now the servers within my network only need to deal with v6 clients, which is nice. That doesn't mean I can do things like go out to GitHub, which needs v4 currently, although they claim to be working on it. We'll see. But now that we have NAT64 set up, and if we use our DNS64 DNS server, everything will just work. Let's demonstrate. So when I create containers before, I used to always pick DHCP and Slack. And so that would essentially get a random v4 address. I didn't care what it was because I was only using it to go out to GitHub. And then Slack, because it would use stable privacy addresses, and I could just copy and paste that into DNS. Nice and easy. But now I choose static. I'll leave it blank, so I get no v4. And then on v6, I choose Slack, so I still get my dynamic privacy address. And let's go. I'm going to say used host settings, which essentially means it's going to copy the DNS resolve.conf from Proxmox. But if your Proxmox server isn't configured to use your DNS64 resolver, you'll have to set a different DNS64 resolver here. So just to kind of show this off, I only have v6 connectivity. I'm going to do an apt update and app upgrade. Then I'm trying to pull a package from GitHub. So I'm not sure if all the Debian repos are v6 enabled. I think they are, but I'm not having any problems with connection no matter what. As for repo, I'm going to try to clone my BPF NAT project. This is a bit of a hobby I started working on a month ago. As with all my hobbies, they come and go. But the goal of this is to implement a client-side NAT46 in eBPF, so it's very efficient. The current implementation is essentially to use Tayga. I'd like to get something that can be merged into systemd, which would be really nice. But if anyone wants to help me on this, I would appreciate it. There we go. So if I just try to get wget github.com, it's going through the NAT64 gateway, all is good. So with essentially no configuration on the Linux server, it's able to process incoming v6 packets, which is all I need, and it's able to go out to v6 and v4 services if it has to do updates or whatever. Everything works just fine. In the modern world, all of these things should be using DNS, so DNS64 should be all we need. But that's not always the case. So let's take a look at some clients where that's not. So that works for everything that uses DNS, which for most people is almost everything you use. If you do Google, Amazon, Facebook, all of them will be very happy to do v6. In fact, most of them are probably using IPv6 exclusively in their own networks, and they don't want to deal with v4 any more than you do. But there's a couple things that slip through the cracks. A big one for me is Discord. So let's demonstrate what that looks like. So I'm over here in my user VM that I use to test VM things. I have v6, but not v4. So if I try to ping quad 9, I get address and network is unreachable. But if I try to ping it through the NAT64 gateway, I get a ping back. So coming over here to Discord, I just logged in. I have a Discord server, by the way, if you want to join me. Link in the description below. I'm on my own Discord server. It's able to load just fine because I'm going through the NAT64 gateway. But if I go to chat here, we get stuck here under RTC connecting. It doesn't work. So what appears to be happening is Discord is fronting all of their stuff through Cloudflare, which is a good way to do things in general, except for their real-time video and audio. That's going directly to Discord servers, and those servers don't have DNS names. So when Discord pairs you with an RTC server to do the real-time bit, it gives you the IPv4 address over HTTP that it wants you to connect to. So the client in the browser is trying to do a direct v4 connection by address instead of by DNS name, so it doesn't get translated. And in general, peer-to-peer apps, especially games, and peer-to-peer video chat apps like this, are really the only things that suffer from this problem. Everything else should be going through DNS. It's not real-time enough to do like peer-to-peer matchmaking. So how can we solve this problem? The way to solve this is with a 464 CLAT CLAT, which stands for Client-Side Translator. So the CLAT creates a v4 address on the local system that it then has a corresponding v6 address, and it does NAT 4 to 6. So the client will pretend to have an address locally in its local routing table. That's, say, I don't know, 192.0.0.4. Usually it's part of the DS Lite prefix range, which is used for this purpose. And anytime an application tries to bind to a v4 only socket, it'll get that address. And that address is a corresponding v6 address to get one-to-one translated. So if an application sends a packet to 9.9.9.9 from its v4 address, it'll actually send it from the v6 address to the NAT64 gateway. And this way, the v4 gets carried over v6 as a native v6 packet. It can just only go to the NAT64 gateway because you can't encode a v4 address, or you can't encode a v6 address in the v4 address space. So a number of operating systems already include this. Android includes it. Mac OS, everything Apple produces includes it. Most of them are automatic. Cellular networks are already relying on this and have been for years. Microsoft will only do it on a cellular network, which is kind of a pain. And on Linux, of course, there are open source solutions. So since I have primarily Apple devices, I'm going to set those up in this video. So now that we've decided a particular client needs a CLAT, how do we get the client to enable its CLAT automatically? This basically breaks down into two problems. First, the client has to recognize that it's on an IPv6 only network and that it should enable its CLAT. And secondly, it needs to discover what the NAT64 prefix is so it can properly configure its CLAT. So for the second problem, we again have two options. The first is a router advertisement option called pref64. If a router advertises this option, it includes the prefix to use for NAT64 logically. This is the preferred option going forward for new deployments, but it's not the only option. The other option is called IPv4-Only.ARPA, and that's a domain name. And it is defined to resolve to two specific IPv4 addresses. So if a client does a quad A lookup and it gets back an IPv6 address, it knows that those well-known IPv4 addresses must have been translated by DNS64, and it can figure out the prefix from that. Now as a network operator, we should be deploying both of these because different clients have different support. Pretty much all clients I've found do support IPv4-Only.ARPA. A lot of them also support pref64, and will prefer pref64 over v4-Only.ARPA. But some software such as CLAT-D on Linux only supports v4-Only.ARPA. Now the first bit, how to get it to enable CLAT, is a bit more tricky. If you just disable v4 entirely, your clients will try to do a DHCP v4 request, is to try to get a router advertisement. And on a lot of operating systems, if they get back a router solicitation and they're able to discover the NAT64 prefix either via pref64 or IPv4-Only ARPA, and their DHCP v4 request times out, they'll enable the CLAT. This is what I used in my previous video when I did IPv6-only testing. I created a separate Wi-Fi network, a separate VLAN that did not have a DHCP v4 server. And that worked. Clients were happy. The downside to this is now I have to create a second VLAN and a second Wi-Fi network for all of my clients that are v6 only. I have to segregate them. And I don't really want to do that. I just want my network to work as a normal LAN. And so that brings us to DHCP v4 option 108, IPv6 preferred. So if a client has all of the software in place to act as a 464 CLAT, it can advertise in its DHCP Discover that support. And that does that by requesting option 108 from the DHCP v4 server. If the DHCP v4 server doesn't support it, doesn't return option 108, client does nothing. If the DHCP v4 server detects that a client supports option 108, then the DHCP server can choose to instead assign the client an address of 0, which is obviously not valid. So this doesn't consume a v4 address from the DHCP pool. And instead, it returns option 108 with the number of seconds that the client should disable v4 connectivity. And during this time, the client will enable their CLAT. Similar rules apply. The CLAT has to be able to discover the prefix with pref64 or v4-only ARPA. But if all of those rules are met, we can get some of our clients to willingly disregard IPv4 and switch to only modern networks. Well, we don't have to segregate all of our clients based on whether or not they support modern networks. We can just have one open LAN for everyone. Now, even if your DHCP v4 server doesn't support this fully, you can still manually add option 108. In that case, the v4 DHCP server will still allocate an address from the pool. So we're not saving addresses in our pool, unfortunately, but we're still turning off v4 on the client side. That's what I've done here. So to figure out how many devices on my network support option 108, I did a packet capture in OPNsense, that's the router that should have all the DHCP requests, and then I analyzed it with a Python script I found on the internet, which told me how many clients requested option 108 in their DHCP request or DHCP discover. So coming over here to OPNsense, we can do packet capture. So we want to capture on LAN, we want to capture v4 only, and we want to capture port 67. And that is a UDP packet. We're going to say unlimited. And let's start this off. I actually let it run for 24 hours to capture all of the DHCP traffic. Hopefully all of the devices that would connect to my network regularly did connect to my network. If you're running a larger network, you'll probably want to run this for a decently long amount of time to make sure you catch transient devices and stuff to get a good statistic. So here's the script I found. This guy who's a member of RIPE NCC, so they should know their stuff when it comes to IPv6. It's pretty simple. You just pass it in a PCAP file and it analyzes it. One quirk I did find is he's specifically looking for DHCP option 1. He's specifically looking for DHCP option 1, which is a discover. So that's when a client doesn't have an address yet. If you're on some sort of public Wi-Fi and you log this for a couple of days, chances are that the clients will always do at least one discover. However, on my home network, clients tend to sit for a long time. A lot of them are wired, things like Apple TVs that are never going to reboot, so they're never going to do discover. So I added option 3 as well, which is DHCP request. That's when they're renewing their existing lease. So with that, I come over here, my modified file. I just changed it to look for 1 or 3, and then we can run it with my PCAP that I took from OPNsense. So it found 59 unique MAC addresses doing DHCP requests. Of those, 13 of them supported option 108, 22%. That's more than the 10 devices I was hoping for in this video, so I just got 13 devices off of the legacy internet. If your network is primarily mobile devices, there's a good chance this will give you higher than 50%. All Apple devices, in my experience, all advertise support for option 108, and some new Android ones appear to as well, although I don't have very many new Android ones to test. So if your network is primarily a guest network with phones, option 108 could help you save a ton of DHCP address space. So here's an example of a packet that has option 108. So 8.1 was requesting a renewal. It's a request. We come to here to DHCP. You can see data request, and it includes parameter request list. So these are parameters that the client would like the DHCP server to return. It includes here option 108, IPv6 only preferred. So when I did most of this testing at OPNsense, I was using version 23.7, which was using ISC DHCP server. ISC has discontinued their DHCP server in favor of their new DHCP server, Kea. So OPNsense now has to migrate from ISC to Kea. And they started that process in 24.1. So 24.1, you have the option to use either ISC or Kea. Neither one of these support option 108, where they don't allocate an address from the pool, but it's on Kea's to-do list, and according to their GitLab tracker, it should be done in about 2 months. So hopefully, by the OPNsense release in the fall of 2024, we'll have full support for option 108, where it doesn't allocate an address from the pool. But we can still fake it. It'll just allocate an address from the pool. But it'll let us test this deployment. So to do that, we come over here to Services, DHCP v4. If you're in an older version of OPNsense, it'll just say DHCP v4. We'll go to our network. We'll go down here to Additional Options. And we're going to add option 108. It is an unsigned 32-bit integer. We can add a value in seconds. So 8600 is 1 hour. So this will basically tell any client that supports it that it should turn off IPv4 and go v6 only for 1 hour. 1 hour later, it'll do a DHCP request, get the same thing back, cycle continues. So unfortunately, the router advertisement daemon version that OPNsense is currently using does not support pref64. So if we look at the additional options here, we're set to unmanaged. We can add additional routes, and we can do RDNSS, but we don't have an option here for pref64. It's not in here. So that means we only have IPv4 only.arpa. So here's where they defined it. So Cisco, Broadcom, Nokia, and they defined 192.0.0.170 and 171. So we can come over here to OPNsense, unbound overrides. So we can add a new host override here. It's going to be IPv4 only.arpa. It's going to be a quad A, and it's going to be 64FF9B 192.0.0.170. And then we'll clone that for 171 and save. So I'm doing a lookup to this DNS server, and it gave us those two addresses. So now clients can figure out that they should be doing v6 only, and they can figure out the prefix. They should be all set. So as an example, on iOS, your IP address shows up as 192.0.0.1 when you're using the built-in CLAT. Similar for macOS. So I know this was a pretty long video, but hopefully you've enjoyed walking through with me on how we're setting up NAT64 to transition to IPv6 only networks, why this is a good transition we should be making as network admins, how we can get rid of our legacy v4, legacy infrastructure, subnetting, all that mess, and stick with nice clean v6, while still being able to provide legacy services for clients. Also, I enabled option 108. All my Apple devices were pretty happy about that. If you have a lot of mobile devices, this could save you a lot of space in your DHCP pools. As I said several times in the video, I have a Discord server, link down below if you're interested. If you want to support me in what I do, I have a Ko-fi as well, link down below for that. Anything is appreciated. And as always, I'll see you guys in the next adventure.